Concavity and the second derivative test, explained by Justin D'Souza. The learning objectives of this lesson are to determine the concavity of a function using the first and second derivatives, to learn the notion of an inflection point and to find one, and the last objective is to find the local extrema of a function using the second derivative test. The keywords of this lesson are concavity and inflection point. Now, before I start this lesson, a quick reminder, if you have not watched the previous two videos, the previous two lessons on the applications of derivative, it would be very hard to follow this. So please go to the description and find the previous two lessons, that is the maximum and minimum values and increasing and decreasing functions. After those two are done, please continue with this video. The concavity and the second derivative test. Now here, you can see this first graph is of an increasing function, whereas this is of also of increasing function, sorry. But can you see there's a difference? From the derivatives, when we graph, we can easily find the increasing, the decreasing functions, maximum, minimum values and everything, and we can graph, yes. But we won't be exactly sure how the structure of the graph will be. Say whether it is concaving upwards or downwards, we will not know exactly. So from this particular concept, the concavity and the second derivative test, we can exactly know whether it'll concave upwards or downwards for increasing and decreasing functions. Now, over here you can see when it's concaving upwards and it's increasing, what's happening? Here, the slopes of the tangent line are also increasing in the sense they are keeping they are positive, positive, positive. Yes, even over here they are positive, positive, positive. But you can see the slope is just more than zero over here, the first slope. Whereas over here it's steeping up in the sense it's increasing, and over here it's very high. It's close to undefined infinity, right? Whereas over here you can see it is very high, it's reducing, it's going on to become flat and zero. So what you can understand is, if the function is increasing itself, fine, but if it's concaving upwards, the slope of the tangent line is increasing, whereas if it's concaving downwards, the slope of the tangent line is decreasing. Now if you recall, we had already found out to draw the basic graph. If a given function is there, we derive it, we get the slope of this tangent line, we find whether it's increasing and decreasing, right? Now the slope of the tangent line, that is the derivative of this, we need to find whether this increases or decreases. That means if we double derive this, double derivation, f double dash of x, now what happens? Whatever the derivative, if it's increasing, over here if it's increasing, then we can tell it's opening upwards because the derivative line is increasing, the derivatives. Whereas if it's decreasing, it is opening downwards. That is what we can do. So we need to do whatever we had studied before, deriving the given function, and then by double deriving we can exactly tell the slope of the tangent line, that is the first derivative of the function, is increasing or decreasing. So that's what is summarized over here. And it also works with the decreasing functions. Okay, this is decreasing, you can see. The last ones were increasing, which we saw just a while ago. And now this is decreasing, going downwards, see. But now what about the slope? Concaving upwards, what we came to know, it should be the slope of the tangent line should increase, right? Let's see. Here, if it's downwards like this, sorry, this line is very close to minus infinity, right? It's very big, I mean very small number. Whereas this line, it's increasing. So now if this is say minus something, it's a very, very big number. And now over here, whatever this number is there, it keeps on increasing. This is now going towards zero. In negative numbers, as the numbers become small, the value is bigger, right? So now over here, eventually it will become 0 and 0. That means it's increasing over here, the slope of the tangent line. So it's concaving upwards. Whereas over here, you can see this is 0 slope. Now it's little less. Now it's becoming more less, more, and very more. That is a simple understanding of the second derivative test. Now let's look into some of the definitions. Concaving upwards means the derived f dash is increasing. That means the derivative of a given function should be increasing. How do we find increasing and decreasing? We need to derive this particular thing, and if it's greater than 0, it's increasing, less than 0, it's decreasing. So that's the thing. Whatever we studied in the previous two lessons must be applied to the derivative now. Downward means it's decreasing, derivative is decreasing. Now, double derivative. Now, directly we can say we'll just derive the function and double derive it, and we can directly explore the given function. And if the double derivative is greater than 0, we can say it's concaving upwards, whereas if the double derivative is less than 0, we can say it's concaving down. We have been given this function. Here you can see f of x is defined. We need to find where it's concaving up and down, and also all the other significant features to graph this. Now how would we do it? First thing is derive this given function f dash of x. What it would be is 3 comes down to be 6x squared plus 18x minus 24. This is the derivative. Now whatever is the derivative, you need to equate it to 0. So it will be f dash of x must be equated to 0. That would be 0 is equal to 6x squared plus 18x minus 24, and then find the x values. So we can use our calculators now. You can press mod 5 and 3 and just plug in the values 6, 18, minus 24. And the values are 1 and minus 4. The x values 1, sorry, I'll write the in ascending order, that's minus 4, and x is equal to 1. Now I leave this over here. You can do it part by part, but what I prefer is I just derive this over here, f double dash of x. What is that derivative? 6 comes down to be 12x plus 18. Now we need to equate this to 0, double derivative, because we need to find this function whether it's increasing or decreasing, right? So it'll be 0 is equal to 12x plus 18. You can use the calculator for this, but it's linear, it's very easy. Just take 18 to the other side, it'll be minus 18, and 12 to the other side, divided by 12 is equal to x. You can simplify, 6 is divisible in both, it will be 3 by 2 or negative 1.5. Now let's do the thing we used to do over in the previous problems. We will derive and find the x value equated to 0, the function equated to 0. These are the x, right? So we will mark them minus 4 and 1. And now we have to take a test value and find whether they're positive, negative, or positive or negative the values are. This indicates whether it's increasing or decreasing. So what you do over here now is, let's go back over here. Let's take test value. Before taking the test value, the derivative, just put it over here. 6 alpha x squared plus 18x minus 24, and sorry, it's 24. And now just calc at any test value. So minus 4 is there, less than minus 4 would be minus 5. Now here it's positive, so I'll just write, we don't want the value, we just need to know it's positive or negative. If it's positive, it's increasing. Next, what is there? Calc a test value over here would be 0, which is very easy to solve. It's minus, so it will be minus sign here, and it's decreasing. And lastly, what do we have over here? Greater than 1, so calc 2 is the test value. Even I can change it to any number greater than 1. I can even put 5. The value will be the value will differ, but the sign will be the same. It's positive over here, so it's increasing. So this is what we found out, right? Let me just erase this and make it a bit smaller, because I have to do one more line just like this, one more simple graph. So this is what is happening for the given function. Now the derived, this is what f dash of x, okay, this is with respect to f dash of x, about this. Now draw another line and put this x value, this is where negative 1.5, so this is 1, somewhere 0, negative 1, 1.5 somewhere over here. That's minus 1.5. Now take test value which is less than minus 1.5 and greater than 1.5. So what I'll do is I'll take a test value of minus 2 here and over here as 0. And now I will have to just use this double derivative equation, 12 alpha x plus 18. Now just calculate at minus 2. What's the answer? It's minus 6. That means here it's negative. That means it's downwards. Okay, no, sorry, I did wrong. From this information, yeah, it is downwards. That is the derivative, the slope of the tangent line is decreasing. So what we can tell for the given function is it will be concaving downwards. It'll be like this. And then what about the next thing? If it's 0 or any other positive number, when you multiply over here, you'll just get a positive number, right? Or if you consider, say, minus 1 also, it'll be positive. Why? Because it'll be, when you solve it, it'll be 6 and so on. So I'll just show you. I'll take any positive number, or I'll take it as, say, calc, just very close to minus 1.5. Let me take minus 1.4. Still, it's a positive value. It might be small, but it's positive. So this tells us that all the side, the right side of this will be positive and it's opening upwards. Now from this information, we can have a more better graph. Let me just erase all this. Now I hope you're understanding why we did the derivative. The derivative is for telling us whether it's concaving upwards or downwards. It's another extra feature of the graph of the given function. Now here, if you are just graphing this, now we know at minus 4, it'll be a maximum point, isn't it? Why maximum? Because it's upwards and downwards. We have studied in the previous lessons. So somewhere it'll be a maximum point, and then over here it'll be a minimum point. But I don't know where exactly it'll fall. How do we do that? That is again from the calculator. To find the exact y values, you should put this given equation, alpha x cube, and over here, sorry, plus 9x. See, only for the given graph, we use this particular equation. Otherwise, if it's after first derivative for this particular thing, we use the first derivative graph. For the concaving up and down, we use the second derivative equation. Only for this particular graph, that's the given functions graph, we use the given equation. That is alpha x squared minus 24 alpha x minus 10. And now calculate at where we need to know what's happening at minus 4. We know it will be a maximum point, but we are not sure whether what's the value. It can be a maximum point even if it's at minus 1, and the minimum point can be at minus 5. It can be anywhere, right? So we can easily find out if you put the calc value as minus 4, it's 102. So I'm not going to draw it accurately to the scale, and even you guys do not need to bother about that. You should just get a realistic figure, that's it. So this is 102 over here. Okay, that's in the positive axis, that's fine. Now what if over here, if it is, say, what's this value? It's 1. Calculate at 1. You're getting minus 23. That means, okay, this is minus 23. Now we have got these two important points. We can accurately graph it, but there are 2 more points which will give you much more accuracy. 4 points, more than enough. Now if you're thinking about the previously, we just drew a sketch because we did not accurately graph it, but now the accuracy increases with this concavity, right? But there are 2 more points. What is the point? This one, that is minus 1.5 and the y-intercept. Now I'll just calc at minus 1.5. I'll tell you why this is an important point in a while. So it's somewhere 39.5 might be somewhere over here. So it'll be something like this. I'll pass downwards. Let's see what is the y-intercept. Calc at y-intercept is 0. It'll be minus 10. Okay. These are more than enough. All these points. What this point tells us is, see this 39.5 is, it's where the concavity changes. It's the point of inflection. So till this point, wherever it comes, minus 1.5 over here, right? Till over here, it is concaving downwards, and it changes its concavity at that particular point. Now let's try to graph. And over here, there is one more thing. So this is over here, we have considered -4. This is 1. It's not that accurate, but that's fine. Over here, -1.5. Now, if you're graphing, we will have more knowledge about the graph. It's coming like this, and it's going downwards until over here. And then it changes its, see, it is passing that and something like this. Okay, this is a very bad graph, but I hope you're getting what I'm trying to do over here. If it's according to the scale, you will get the most accurate graph. But over here, let's see this point, -4, because it's increasing and decreasing. It's the maximum point, and that's 102. Then it'll pass through the inflection point. That means the concavity stops. Over here, it'll stop. And then from here, this point onwards, you can see it's opening upwards. Concavity is upwards. But we know the intercept is -10, so it'll touch somewhere over here. Okay. And then this is the minimum point, 1. Why? Because it's decreasing and increasing. Whenever there is decrease and increase, it'll be the minimum point. So that's how we can graph it. Now, if you see the final graph, let's just quickly see over here. It's not that accurate, but still you can see there is some accuracy in it. Okay. Now, one second. This point of inflection is at -1. Okay, I've done a mistake. See, I've written this 39.5 and I just took it like this. See, this point of inflection is at 1.5. Over here, this is the point of inflection. I've marked this point and then it'll go like this. Okay, that's my bad when I was going through the points. See, over here it's mentioned somewhat over here. You can compare these graphs. They are much accurate now. So this is why we take all the information. Now this information, left side, whatever we have done, this particular graph is the most crucial one. If you do this, it's the same thing what we'll be doing for each problem. So please be thorough with this particular table. You can call this as a graph or a table, it's fine. So we will move on to the next one. But before that, there's a definition that is about the inflection point, the point of inflection. That is where the concavity changes. If it's concaving upwards and then it will change to downwards, or if it's downwards and then to upwards. That's about it. And over here now, determining concavity, again the same thing. We will just do it. Now, if you follow the method which we did just a while ago, any problems can be solved using this particular method. Now, first thing is deriving f dash of x. What happens? The 4 comes down and it'll be x cubed minus 2 comes down over here. It'll be 12x and 1 is gone because it'll be 0. Now, I'll directly do it. This f dash of x will be 0. So it'll be 4x cubed minus 12x equals 0. Now, we can use the calculator and solve it. But before that, I'll just do the double derivative as well. Double derivative is just deriving this. It'll be 12x squared minus 12, and that also is equated to 0. It'll be 12x squared minus 12. Now you don't need to simplify, take the common terms or anything. You can directly use the calculator and solve now. Let's do this first. It is mod phi, and now the cubic functions are given by, cubic equations are given by mod phi 4, and let's substitute the values. Before x cubed it was 4. Is there any term for x squared? B is for x squared. Now if you go via mod phi, before pressing 4, you can see b is the coefficient of x squared. There is nothing, right? So it's 0. B value is 0. What is the coefficient of x? It's minus 12. Don't forget the sign. And lastly, the constant is 0. So the values are √3, minus √3, and 0. There are 3 values. So let me just draw a line. 0, positive √3, negative √3. So x is equal to plus or minus √3, 0. Okay. Now over here, the next one also you can easily find it out. Mod phi and 3, 12. There is no x term, so it's 0. B over here in this case, b is the coefficient of x. And last one is the constant term, minus 12. And the answer is 1 and minus 1. So from the second derivative, we got 1 and minus 1. Let me just draw another line over here. See, now this negative √3 is 1.73. So it will be within this minus 1. Minus root 3 is minus 1.73 somewhere over here. Then we have 0 and this is 1. So x is equal to plus or minus 1. This is the information we got. Now we need to choose test values and find whether it's positive or negative. Now let me just write, this is f dash of x, this is f double dash of x. So whenever you choose a test value, don't put it in any equation. The first line over here, this first table or this graph is for f dash of x. Oh, it's best to say number line. That was the word which I was looking for. It never came to mind. Okay, the first number line is for the first derivative, whereas the second number line is for the second derivative. So any test value in this, you put it over here. In the first one, in the first derivative. So that's it. Now I will write this equation as it is. I will use alpha x. Why? Because then you can easily use calc and solve the values. Otherwise you need to put the test value instead of x. Now easily you can just change calc, change the value from minus 2. Why? Because root 3 is negative, minus root 3 is negative 1.73. Now minus 2 is less than that. Over here we got negative, this is minus. Now let me do calc at minus 1. Positive, negative, positive. Let's see the next one. Calc at positive 1, again negative, and last one would be positive. So this was positive, negative, positive, negative. That means it's decreasing, increasing, decreasing, increasing. There is a minimum point here, maximum, minimum. Now what about the next one? All you need to do is change this equation to the next equation, to all alpha x squared and then minus 12, and over here you need to plug in these two values, right? So how you do is basically calc, not these two values, less than them. So I'll do calc minus 2, that's positive, and I'll do calc plus 2, positive. So both are positive in this case, and here it's, oh I forgot, this is positive, positive. I forgot to do the middle part, that is 0, that will be negative over here, calc 0, and that's minus. So the middle one is minus. So what's happening here is basically concaving upwards, downwards, upwards. This is the basic understanding of the graph. Now then, if you're graphing this, here we need to mark some important points. That is minus root 3 somewhere over here, 0. Here we have plus root 3. Now we have minus 1 somewhere over here and positive 1. Okay, it should be, anyways, it's not that accurate, but anyways. Now what you need to do is put this given equation in the calculator. Just alpha x to the power 4 minus 6x squared, and lastly we have plus 1. And now calculate at these values, not before and after. We need the exact values over here. So calculate at minus root 3, that is about negative 8 somewhere over here. Let me take minus 8 as over here. Sorry, I don't need to write minus 8 over there. I just need to write it over here, minus 8. Then calculate it at minus 1. It is minus 4 over here somewhere. And now let's calculate it. Calculating it at 0 is plus 1. It's easy, 0, 0, so it's 1. And now then we need to do it for plus 4. That is 161. Okay, the scale is crazy now. Okay, this is 1 and this is 161, which is not so true. Okay, 161, not over there. These are the important points for the graph. Okay, they are very handy for the graph. Now last value is at root 3, positive root 3, and it's at minus 8. That will be over here. Okay, somewhere over here the graph touches. Now then, I forgot to draw the points, which was very silly of me. But anyways, I know them. It was over here -8. Then over here it was 4, and then over here this point. Then at 1 it is this point, and lastly we have again -8. So graph will be somewhere over here. Now then, after this, we forgot. Did not forget the intercept because 0 is already mentioned. So we have the intercept by itself. Okay. Now, see, we are not doing the exact details, but we can see some things. Now, what are they? Here, before -3, it's decreasing, and then after -3, it's increasing. And we know it's like this. So, this particular graph will have something like this over here, the first one, because it's opening upwards, and then like this. This I can be sure of. Next, it's concaving downwards. Okay, let me just check this. I'm sure that whatever I did over here is wrong. Why? Because the information of the graph, see, these tables tell me my value is wrong. This 161, I just realized it now. X is equal to 1. See, it's -4. Okay, it should have been all symmetrical, but anyways, I don't know how I wrote that. This is the value over here. See, now this is so important. With this information, you can easily deduce what is wrong, what is right. Why did I tell that is wrong? Because I know it's going downwards like this, and it increases over here and it touches over here. That's the thing. Now again, this is happening over here. This is the maximum minimum points. Yeah, this should minimum. Then something happens over here. Okay, now why I can tell it's going up, I know it's concaving upwards and it's increasing. So it's increasing like this. Now this is, now it should touch at these points, but you know it's not that accurate. But this is the graph. It will be something like this, similar to this. Now if you do so much, now not this one, that's wrong. Okay, if you do so much, that's correct. That's how the graph should look. Let's just look into the final graph over here. You can see it's like this. So you can see it's not absolutely accurate, but very, very accurate. So this is how we do it. And now you can just follow this method. First derivative, second derivative, the number line for the first derivative, number line for the second derivative, and the graph. That's it. This can be done for all the problems. Now over here, that's it. See, we have a problem here where there is no inflection point. In the sense, let's understand what is x to the power 4. I'm sure you know the graph is parabola. There is nothing plus or minus. So x squared is something like this, positive x squared. X to the power 4 is something like this, right? Parabola only, okay? But it just be flatter at the down. As the power increases over here, the even number increases, it'll be more flatter. Now you can see the graph is something like this. Is there an inflection point exactly? So it's opening upwards itself, right? It's not opening up and down. So there is no inflection point. This you can just see over here by derivative. You will get f double dash of x equals 0. We need either positive or negative. But no, we are getting 0. So over here, that's why we can say there's no, sorry, what I'm trying to say is when we do the table, let me just do the table quickly. Let me just take this off. When we do the table, you'll understand the relationship. Now, first over here, derivative f dash of x is equal to 4x cubed. And double derivative of x is 12x squared. Now then, we have to just equate it to 0. 4x cubed equals 0. That is x equals 0. Over here, it will be 12x squared equals 0. That is x is equal to 0. Now let's just do this number line for the first derivative of x. Here 0. We'll take a negative number. If you put a negative number, the negative number sustains. It'll be minus. Here right side will be plus. So it's decreasing, increasing. Now what about double derivative? 0 itself. This is 0. Let's take a point. Now here, what's the thing? Derivative is 0, x squared. So it doesn't matter you take a negative point, minus number or positive number. It will just be positive on both the sides. Why? Because you see, you put a minus number inside square root. inside power 2, it'll be positive. So this will be positive. Even if you put plus number, it'll be positive. So it'll always open upwards. So there is no inflection point. That's the thing over here. Now that's the reason, and you can see the graph at 0 over here from this. See, you can't use this. This is like a redundant information over here. Just from the first derivative, you can understand it'll come down over here, minimum peaks, and goes up, increasing. At 0, it is the minimum point from the first derivative itself, and it is upward. So this is how we can, and this is how sometimes whenever this x is equal to 0, because this x was 0, we have to go back to the first derivative itself. From this, we are gaining information, not from the other way around. So I hope this is clear. But such problems, it's very easy. If it's a simple graph, right, you can easily understand how the graph. But whereas in the previous problem where the graph was a bit complicated, look at this, it's very complicated. It's not easy to understand without a graphing calculator or this particular method where you need the number line both the first derivative and second derivative. Now there is one more bit of information. Wherever there is concaving downward graph, there will be a maximum, local maximum. Whereas if it's concaving upwards, there will be a minimum. You can see this is the figures and you can see the minimum maximum. So this is one more useful information. And you can see that if it's f derivative, this is less than 0. That is what it is, concaving downwards. Okay, so that will have a maximum point. You can see this is concaving downwards, maximum, this minimum in terms of theorem. Now it's again the same methods. Now we will just go through this problem quickly. What I would highly suggest is you guys please try solving this by yourselves. Do the methods. I'll just quickly write down the methods. You need to derive f dash of x. You need to do f double dash of x, and then do the number line of f of x, f double dash of x. And you will get whatever the x values put it, do both the number lines, and then easily graph it. You don't need to go to any other different methods. You can stick to the same method and you can solve all the problems. So what I would highly suggest is instead of changing the methods every now and then, just stick to the same method and solve it up. Over here, you can see the first derivative, second derivative, and then this is the graph. And now over here, they have not done the number line. They have directly done, because they have just asked you to find local extrema. Okay, that's the reason. They've just asked you to find local extrema. So you directly do the second derivative and check whether it's greater than 0, less than 0. Over here, it's concaving downwards. So this is local minima, maxima, minima. But the best, I think so, we solved it just a while ago as well, the same problem, I guess, I'm not sure. But anyways, the most important thing is if you follow this, you will definitely get all the details. Now here they have not asked you to graph, that's why you do not need it, but better to do the entire method for your practice. Now remark over here, if f double dash, the second derivative, is equal to 0 or undefined, the second derivative test yields no conclusion. So this is one important thing at any particular point. Over here, we can't understand anything. So we need to use the first derivative itself, what we have been doing in the first part, and then we need to extract the information of the graph. We can see some problems over here where the second derivative test is inconclusive. See, we have done x to the power 4, same way x to the power 3. It's a cubic function, right? You don't even need to directly, you can graph it out, but you can see here at this particular point, the double derivative, what's happening? Double derivative of 0 is 0. So over here, we can't rely on this. So if you do that particular steps, right, you will realize over here it's 0. So in this case, it may or may not be. So you can't rely on this. You can rely on the first derivative and you can say how it is reacting. So this is the thing. But over here, this graph is very easy. Even the next graph is very simple to understand. It'll just be at -1. It's a parabola, just like what we have done a while ago at -1, like this. We have done just a while ago we had done it. So you can see from there, the second derivative test is inconclusive. So you need to stick to the first derivative itself and it'll be down, up. So this is the minimum point. And the last one is over here. That is x to the power -4. It's the same thing just a while ago, but minus means it'll down, it'll go open downwards, and it'll have a maximum point. That's it. Even over here, second derivative is inconclusive, so you need to stick to the first derivative itself. And the last problem over here is of a rational function. Now, same thing, same method. Let's just quickly try and do this. F dash of x. Let's derive this. Just that it's a rational function, it'll be undefined values. Now, how do we derive it? It'll be 1 plus, what's derivation of 1 by x squared? 1 by x is negative 1 by x squared. So I'll directly use the formula. I will not do the steps of, taking it up. It'll become the power minus 1 and then solving. You can do it if you want, but I'll directly write the answer. It'll be minus 1, but the constant is 25 by x squared. So this is the derivative. Now we need to get into rational function, numerator and denominator, right? So solve this. Over here now, since it's x squared, it's very easy. You're multiplying up and down by x squared, and the denominators will be same, x squared. And over here, 1 becomes x squared minus 25. This is the thing. Now, whatever is in the numerator needs to be equated to 0, and the denominator as well. Whatever is this, that is just normally equating to 0. This is undefined value, and find this as well. So what you get over here is, see, this can be easily, you can use your calculator mode 5 3, but you can see this, just take 25 to the other side and square root will be plus or minus 5. So from here you get x is equal to plus or minus 5, and from the down x is equal to 0. Same thing, you need to derive this for the second derivative test. Now don't use this derived one, you will have to use quotient rule and it becomes longer. How about use this particular function? It's very easy, right? Because the first term 1 becomes 0, you're remained with minus, I'll leave this 25 for now, it'll be 1 by x squared. Do you know the derivative of minus 1 by x squared? The sign changes to plus, it'll be 2 by x cubed, isn't it? Because I know it for plus 1 by x squared, it is minus here, okay? If it is 1 by x squared, the derivative formula is minus 2 by x cubed. So I'm directly using it. Otherwise, you can take this up. It'll be minus 2, then solve it. You will get it. I'll directly write 1, minus and minus becomes plus. 2 times 25 is 50 by x cubed. Now, all this we have done in the previous lessons on derivatives. You need to be very thorough in derivations, and then you can easily get this. So, my bad. I've written 1 over here. 1 dissolves to 0. So, this is the derivative. Now, this is undefined. Over here, x cube is undefined and just equated to 0. So, x it's really not equal to, but we do it in the number line. We just write it in the number line as well. So we have to do the number line now. F dash of x number line is with all these points minus 5, always in ascending order, 0 plus 5, and f double dash of x number line is with only 0. Okay, you need to take test values now and check it out. So let's take out our calculators. All you need to do is put in this function derivative 1 minus 25 by x squared, and now calculate it at less than minus 5 is minus 6, and I'm getting a positive value. I'll directly do the others as well, and I'll calculate at minus 4, I'm getting a negative. It's plus, minus, let's see what next. Let me just take it as 1, plus, minus, minus, right? So we got plus over here, then we got negative over here, also there's negative. And let's see the last one. Calc more than 5 is 6, it's another plus. So this is the thing. And over here we have got 0. See, now this second derivative is inconclusive, you know that, right? Why? Because it's undefined over here. But even if you do this, let's take value before 0 for this particular thing, 50 alpha x cube, sorry, and calculate it at, not that, sorry, cube, I'm just doing blunders after blunders. Alpha x cube calculated at -1. You can choose any other negative number. It's negative over here, and I'll just calculate it. It'll be positive over here. So minus plus. Sometimes I just did that. It's so simple over here. Odd power, the sign sustains. You could have directly taken it as well. Now here that means it's downwards, upwards, increase, decrease, decrease, increase. Now this is a rational function. You know this is both undefined over here. That means in the graph over here there will be undefined. It's an asymptote. Okay, there are various ways to find the asymptote, but before that, let me just draw the graph over here. Now, one of the ways would be, taking the limit. If you take the limit, you will realize this is undefined. These points are undefined at this particular line. So you basically just leave that because there's an asymptote over there from rational functions we know. So what I would do is, this is concaving downwards and will have a maximum point. So you can just substitute over here the x, any one x value, say this -5, and check. Now I'm not going to do entirely because I know if I put -5 over here, it's going to be -5, and this also becomes -5, it'll be -10, so it'll be negative directly. So it'll be in the negative quadrant. The first part, it's increasing at -5 here. It'll be something like this, and then it goes down. Okay, and what, because it's concaving downwards, it's not accurate, but that's somewhat what it'll look. Over here it'll be +5, it'll be something like this. So this is the answer. It's a rational function. Sorry, that's not accurate. It'll be something like this. Okay, it'll just go that side. Okay, over here it doesn't dip down, it's something like this. It depends. If you take more points and just find it, you will understand more better. You can see the final answer in the graph. Say it's something like this. Okay, not accurate, but you can understand. That's how it is. Okay, from these informations we're getting, it'll be one part over here, one part over here. Minimum point is at +5, and maximum is at -5. This is the information. So over here, from the limits, you can easily find out as well how it is reacting. Okay, there is one more problem. I thought that was the last problem. It's the same thing, same method. So please do it by yourselves. Now, first thing is you need to find the derivative of this. When you find the derivative, you get this. Now here, they have not written properly. Really, what happens? Power is negative, right? Because 1/5 derivative will be -4/5. So you need to write it as 5 into x plus 2 the whole power 4/5. So it's the denominator. Over here, this value is undefined value. Just equate this to 0. X plus 2 equals 0. X is equal to -2. This is the undefined value. Basically, x cannot be equal. Okay, it's not equal. But we take that x value. It's important. So that is the thing. Now, when you derive this again, what happens? Now here, this comes down. It will be -4/5. 5 times 5 is 25. So -4/5 x. Again, -1. It will be 9/5. Now again, this will be written as -4/25 x plus 2 the power 9/5. Again, over here, you need to equate it to 0. You will have undefined value. Okay, at x is equal to -2. So over here, the limits are from -infinity to 2 to infinity. Okay, that's the thing. You can find over here the first part, it concaves upwards, downwards, whatever we did. You should just do the two number lines and then you'll find it out. And then over here, look, they have found the derivative. See, there is the graph is something like this. Okay, now over here there'll be a problem. Why? Because if I just show you over here, this is increasing in both the sides. Now this is -2, right? For the first graph. The second graph is very easy. I'll just do the first number line, f dash of x. Over here we have -2. So take a test value and substitute in this. I'll show in the calculator. We will take a test. First, let's substitute this over here. It's 1/5 You can write anyhow. You can write in the denominator, or you can write it with the power negative, plus 2 to the power minus 4 fifth, or 0.8. Now here calculate at x less than minus 2. I'll take x as minus 3. I'm getting a positive answer. Let me take more than minus 2. Say I'll take 0. Obviously, I'll get another positive answer itself. Calc at 0 or any other positive number, you're getting positive number. So what is happening? It's increasing in both the cases. It's increasing over here, increasing over here. So you can see it just going upwards. But we saw over here at minus 2, if you substitute x values less than minus 2, here it is positive. If you substitute greater than 0, minus 2, it will be negative. So f double dash of x, if you do that number line at minus 2, here we got plus and plus, increasing, increasing. Here what happens is it's plus and minus, so it will be concaving upwards and concaving downwards. So therefore we can easily understand the graph at minus 2. It's coming like this and then something like this. And now if you want to know why it's like this straight over here, if we take the limit on this derivative, that is the slope of the tangent line of the given function, right? You can see it's going infinite. That means slope is infinite, means it's a straight line, right? If it was a flat line, slope is 0. If it's a straight line, slope is infinite. So that's one more thing. But you don't need to do all that, just the rough approximate. Just by the, from these two, you can get the rough approximate and just substitute the values over here at these point. You will get the values and you can roughly graph it. That is more than enough. So that is how we do it. And from this limit thing, we'll just get the tangent line is at minus 2. So it's a straight line over here. That's the end of this lesson. I hope you have found it helpful. Please be thorough with the previous two lessons, that is the maximum and minimum values and increasing and decreasing functions, and then this will be just a continuation of those two lessons and will be much easier. That's it for this lesson. Before you go, please do subscribe to my channel. It would mean so much to me. And also do like and share my videos with your friends who might find it helpful. And until the next video, take care and happy learning.